Assalamu alaikum. My name is Moaaz Ahmad and in this video I will be discussing the DLD Lab 8. In this lab we were assigned to design four different circuits which are half adder, half subtractor and full adder and full subtractor. So first of all, this is the truth table of half adder circuit, and now we can see here that there are two inputs and two outputs in this circuit. So if both the inputs are 0 0, then the output will be 0 0 on the both ends. And if B input is 1 and A input is 0, then we can see that S output will be 1 and C output will be 0. So if I go to my Proteus file, which is right here, and I can see that this is my half adder circuit, and in this circuit I will be using XOR and AND gates. So if I run the simulation from here, and I can see that since both of these switches are on, and if I open the truth table right here too, and I can see that if both the inputs are on, then C output will be on, so D2 is on. But if I change it to something else, say let's implement this, so let's say I implement this scenario in which B input is 1 and A input is 0. So let me change this to 0, and now we can see that D1 is on but D2 is off. So it's following the same pattern according to our truth table, so we can say that this is true. So now if I change to the second variant of this circuit, which is implementing this circuit using NAND gate only, so we can see right here, if I run the simulation here, I can see that since both of these inputs are off, that's why no LED is on. But let's say I change this input to 1, and I can see that now D1 LED is on but D2 is still off. So let's try turning on this one too. So if both of these inputs are on, then D2 LED is on but D1 is off. And if I turn the input 1 off, I can see that now D1 is on but D2 is off. So that is half adder circuit using NAND gate only. Now let's see the second circuit we were assigned to implement. So this is the second circuit, half subtractor circuit, and we can see here that it also has two inputs A and B and two outputs. Now since both of these inputs are 0, then both of these outputs are also 0. But if one of these inputs, let's say A is on but B is 0, then we can see here that D will be on but the other output will be off, 0. So let's implement the same circuit in Proteus. So this is our half subtractor circuit using XOR and AND gate. Now if I run the simulation here, and I can see that since input 1 is on but input 2 is off, that's why both of these LEDs are on. And if we go to our truth table here, and this is the scenario it's following. Since input 1 is off right here, but input second input is on, which is right here, that's why both of these outputs are on. But if I turn on both of these inputs, which is the last scenario, then both of these outputs will be off. So let's implement this. So if I turn this on and or change its value to 1, and I can see here that both of these outputs are off. So that's our half subtractor circuit using XOR and AND gate. Now coming to the NAND gate only part. So this is our half subtractor circuit using NAND gate only. So if I run the simulation from here, I can see that since both of these inputs are 1, that's why none of the LEDs are on. But let's say if I change the value of this input to 0, and I will do it. Now both of these LEDs are on, but if I change both of these inputs to 0, then none of the LEDs are on. So that's how the Hall subtractor circuit using NAND gate only works. And now let's move on to the third circuit, which is full adder circuit. So in this circuit we have 3 inputs but 2 outputs. So we can see here that since if all the inputs are 0, then both the outputs will be 0. But if all of the inputs are 1, then both the outputs will be 1. So other scenarios are also given here. So if I go to my Proteus file right here, I can see that this is my full adder circuit using XOR, NOT, OR and AND gate. So this circuit is using 4 types of gates, and if I run the simulation from here, I can see that since all of these inputs are 1, that's why both of these LEDs are on. But if I change one of their values to 0, let's say I change the value of this one to 0, now only D2 is on. So let's compare it to our truth table. So this is our truth table for this circuit, and let me just adjust it a little bit. So this is good. So we can see here that the input A is 0, which is this scenario. Input A is 0, but both of the other inputs are 1. In that case, the first output will be 0 and the second output will be 1. So the same case is implementing here. D1 is 0 but D2 is 1. So our circuit is working fine. And now coming to the second variant, which is using NAND gate only. So this is our full adder circuit using NAND only. So if I run the simulation here, I can see that if the one input A is 0 but both of the other inputs are 1, then D2 is implemented, is turned on. But if I change the value of all of these inputs to 1, and then the D2 is still on. But let's say I change the value of the middle input to 0 and also change the value of third input to 0. Now I can see here that only input A is 1 and both of the other inputs are 0. That's why the D1 is now turned on instead of D2. So this is our full adder circuit using NAND gate only. Now coming to the last circuit, which is full subtractor circuit, and truth table of that circuit is right here. I can see here that this circuit also has 3 inputs and 2 outputs. Now if all of the inputs are 0, the output of these circuits are both 0. But if 2 of them are 1 and the third input is 0, then both of the outputs are still 0. But if only the third input is 1 but A and B inputs are 0, then both of the outputs are 1. Now if I go to my Proteus file, which is right here, this is my full subtractor circuit using XOR, NOT, OR and AND gates. So if I run the simulation from here, now since all of these inputs are 1, that's why both of these LEDs are on. So if I compare it with my truth table right here, and let me just adjust it a little bit, and that's correct. So I can see here that since all of these inputs are 1 and it is 1, so both of these outputs will be 1. So both of these LEDs are on. So let's say I change both of inputs A and B, which are these two inputs, to 0, but I keep the third input to 1. So let's implement the second scenario from here. So if I change the value to 0, 0, Now both of these LEDs are still on, which is exactly according to our truth table. This is our full subtractor circuit using XOR, NOT, OR and AND gate. Now let's implement this using NAND gate only. So this is our full subtractor circuit using NAND gate only. And if I run the simulation from here, and I can see that, see, if all of these inputs are 1, then D2 will be on. But if I change the input of both of these inputs to 0 and keep the third input to 1, then D2 is still on. But if I change the input of this one to 1 and this one to 0, then D1 is on. So that's the full subtractor circuit using NAND gate only. And that's it from this video, and till next time, Khuda Hafiz.